As I told you just before the break, I want to take some time, 1 hour, something like that, to speak a little bit about the other component of the lighting system, which is the fixture. The fixture is a very important component, but is more related to the optics of the system, but has a huge influence on the lighting system design, much more the ballast or the driver. For you, the ballast and drivers are more important, but ballast or driver, the only thing is the possibility to play with the light and reliability of the system. The fixture has a much more important influence on the design. First of all, what is a fixture? Well, what is first of all a fixture or a luminaire? There is a standardized, you see everywhere I'm speaking about standards. There is a standardized definition of the fixture, which is a device for distributing, filtering, or transforming the light from lamps, comprising all the parts necessary to fix and protect the lamps and connect them to the power supply. The fixture can contain or not the power supply. This is not a part, but contain all the other parts that they are necessary to protect the lamp, to supply the lamp, and fix the fixture somewhere. We speak here only about indoor lighting. For outdoor lighting, the specifications are sometimes different. And in a building, we can find different kind of fixtures. We can find suspended or fixed fixtures in the ceiling. They are just on the fixed there, or from a distance from the ceiling. Can be recessed in the ceiling. This is the case here. Can be fixed on the wall. Okay. Placed on the work surface. You put your lamp on the table to see what you are doing, or placed on the floor. This is something that we'll find mainly in our homes or in some other places, not very often in office spaces. There are the components inside a fixture. This is not limp. Yes, this is the box, the external box protection. Then you have a reflector. This reflector can be very high quality, using glass with silver layers is the best that we can find today, or it can be plastic with reflecting surface, or it can be just a piece of aluminum or iron which is a little bit polished. It's again a question of price. Then you have the lamp, and you may or not have a transparent cover, and you may or not have this kind of slats, which is the anti-glare, is to avoid to see direct. When we speak about glare tomorrow, you understand why we have these slats here, so to avoid to see the lamp directly and be glared. And the function of the fixture is to shape the beam coming out from the fixture. This is a very general classification of the different fixtures. They can be direct and indirect or mixed, and they can be extensive or intensive. Extensive means that we'll define that the beam coming out from the luminaire is rather large. Intensive, that means the beam is more like a projector. Okay. How you can define better those things? How you can define the beam shape? We use for that the photometric curves. the photometric curves, I remind you that we spoke about that in the second sequence, in the second lecture. We can measure that with a photogoniometer, which is a very specific instrument turning around the lamp. Here is not the lamp, but is the global fixture. That means you need even a bigger photogoniometer, and you can acquire all the necessary data to build this photometric solid in any angle around the fixture or the lamp with a step of 5 degrees, angular step 5 degrees minimum. And then if you can take a cut of this photometric solid, you obtain that we call the photometric curve. And this photometric curve is not just a picture, but you can use it in principle to obtain from the curve the intensity, the luminous intensity going to a given direction. If you take this photometric solid, that cut, there is the cut, I put it here. If you take the axis here, you see 1000, 2000, 3000, and then you have the directions. In fact, 1000, this is candelas, 2000 candelas, 3000 candelas, 4000 candelas. That means if you take a ruler and you measure the distance from there to there, that is equal to 1000 candelas, you have your calibration, and then if you measure from there to there in direction of 30 degrees, you can find here you have 3000 candelas. That means if you have the candelas in all direction, and I remind you that the intensity is df over d omega, the angle, the differential variation of flux over the solid angle. If you take all the points here, even manually, you can calculate the integral and you can find the global flux of your lamp, even if your manufacturer doesn't give you the flux. This kind of curves, either in a curve form or today more in a electronic version, they are absolutely necessary in order to make photometric calculations and make sizing of lighting installations. Yes. The intensity is the distance from there to there in a given direction, and this is for any cut. Okay, your device, one is situated here, measure, for example, the intensity, which is equal to that at 60 degrees for that cut. Now it turns around, depends if it is symmetric or not, is the intensities in one direction in all the space. Okay. These measurements, they are done by using also standards. You don't do the measurements as you want. And as I told you, this kind of values today, you will get it in a numerical format that we call the photometric files. And the photometric files, there are two types, the .ies or the .ltd, but the .ltd is proprietary, forget it. .ies give you inside the file all the intensities. In fact, the file itself, you can edit it. It's in a text format. You can read it, and you have a given type of information at the beginning, and you have here the values that allows you to get the photometric curve in a given cut. These kind of files, they are provided by the manufacturers. The manufacturers of the luminary, and you have some freeware, software this one, for example, that can absorb .ies file and show you what is the beam. And even if they have 3D information inside, you can see that in 3D. Well, as I told you, those files, they are used by simulation, lighting simulation software. There are two kinds of software. One is called Dialux and the other is called Relux. Both of them, they are used by all professionals and they are absolutely freeware, because has been established by a consortium of industry, and the idea was to abolish publishing such kind of information in paper format. They provide now in a numerical format, and they provide a software that is able to use this information and tell you how many lamps you need to put, for example, in that room in order to obtain a given value of illuminance in your table. If you have a manufacturer, fixture manufacturer, that doesn't propose this IES file, is not a good manufacturer. Forget him, never buy anything to him, because you absolutely need that information in order to be able to size your lighting system. If you don't have it, you cannot work with this manufacturer. And sometimes we find also some manufacturers that they propose generic files that they have nothing to do with the reality. The problem with a manufacturer, to get a such file, they have to go either to have by their own an accredited lab, or they have to go to an accredited lab to get this file, and this may cost more than €1,000 per file. If you have 100 products, you have to spend €100,000 for having the ES file for all your fixtures. But without that, equal non-reliable manufacturer, put him aside. The use of such information of photometric files is very old, even before the beginning of computer era, with all people can have a computer today. In 50s, it was not the case. Those people, they wanted to limit the number of necessary data for describing a single fixture, and they define two plans. One is the cross-sectional, and the other is the longitudinal plan. Why they are plans? Because you have this side and that side. If your fixture is symmetric, this part is the same here or here. If your fixture is not symmetric, it may change, and those plans, we call it C0 and C180 and C90, C270. This is the minimum information that you have to have inside the IES file. If the fixture is not symmetric, that means has a directional flux, in that case, normally you have to get another C plan. I don't know which one, but say if the maximum of the lamp, the fixture is at 30 degrees, the manufacturer has to give you the C30 and the opposite plan in order to be able to make better your calculations, because your fixture sending more light to a given position. We'll see some examples after. Those two plans extracted from the photometric solid, we call them the polar intensity diagrams or plots. This is the official name, and usually in an old paper version of fixtures manufacturer catalogs, you will find it in that format. You have a single polar plot. One, the yellow here is for the longitudinal, the C0, C1 80, and the other, the dotted, is for the transversal, for the cross-sectional, sorry. Cross-sectional is yes, for the two plans. You have the information for the two plans. Sorry, sometimes I always I'm thinking which one is the right, which one is the other. Well, just take that, and same information here. If you take your ruler, you can measure from there to there, for example, and say you have 1, 2, 3, 4, 5, 6, 7 lines, and each line is 1,000 candelas. That means this fixture in that plan here emits 7,000 candelas. Is the equivalent of 7,000 candles. And on the other plan, it takes the same direction, is the equivalent of 1, 2, 3, 4, 5, 6 point something candelas times 1,000. And this is given, be careful, this one is given in candelas, but sometimes can give in candelas per kilolumen. If your fixture gets out 1,000 lumens, is okay. If you have 10,000 lumens, you have to multiply by 10. And if you have 500 lumens, you have to divide by 2. Okay. You have to read very carefully. If you use these plots manually, you have to read very carefully what is written for those plots. Yeah, there is some examples. You see, this is you have beams, and you have symmetric, and here you have an asymmetric fixture, and you see, by using the different beams, you can decide how to light up different spaces. Okay, this one will create a spot. That one, if you use it in that direction, creates a line, or well, it depends how you put the fixture. And here is also something interesting. When you look at the desk here, this is very bright. This area is less bright. It depends on how you choose the luminaires above, and that you have to know is many lighting standards impose at 80% uniformity on the desk. That means here I don't have 80% uniformity on the desk. I have more than 20% more light here than there, otherwise I cannot observe it. And this is mean the choice of my fixtures above. Most probably they are not compatible with the lighting standard. It's not a good choice. Examples to understand here. I want to have uniform lighting in the working desk. Here is a configuration of cubicles that you can find, for example, in US or in Japan. And you have also a corridor here, and people has to walk. Look for here we select, there are the fixtures. You see 1, 2, 3, 4 lamps visible, and a part of the flux is going upwards and come back from the roof. And this luminaire, there is the polar intensity diagram. If you take the cut that way, this one, you see the 4 lamps. And if you take it that way, it's very Lambertian, and you see that also a part of the flux is going upward, following the two plans. When you see that you have a fixture that in that plan open the beam at 60 degrees. And the high is not very so high. That means here, as the distribution is very constant, means that you can eliminate very effectively and with a good uniformity just under the luminaires. Here you have one here, one there. That means by using that luminaire you can have a good spatial uniformity that is requested by the standard in order to have the best visual performance. And you may have different here to eliminate the street, the corridor. This is another example. Here, this is a design office. The guy needs a lot of light in his desk. If you put the lights here, you will be in trouble because you will see the lights. Then you put the lights behind him. And of course you use fixtures sending the flux here. Okay? You illuminate from behind, and you can even choose the angle of the maximum illuminance to the direction here in order to avoid, for a standard high worker, the shadow from his head. That means the flux pass above him and then illuminates very well his working plan. You see what I said between uniform and non-uniform. For example, when you go to some teaching areas, you have the white board or the black board, and sometimes you have headlights above the board to illuminate only the board and not glare the teacher or the students. They have exactly the same structure. That means in that direction they send the light that way. In that direction they send the light to a uniform way in the space. That means if I take any cut here, I have the same quantity of light arriving. And now if you take these photometric curves, these plots, then you can define much better what I said at the beginning, the direct and direct, or direct and direct, semi-direct and things like that. You have here the different real classification of the different fixtures. And here, following the denomination, that means how much flux percent is going upward and how much flux is going downward. That means if I have a direct fixture, I can allow up to 10% of flux going upward. If I have more than 40% of flux going upward, then I am in the configuration of semi-direct. Okay? That means if I take a catalog, I don't need to see that curves. If the manufacturer told me this is a semi-direct or a diffuse, immediately I know few percent average how much is going up, how much is going back. Sending light above, what is the interest? When you illuminate the ceiling, as the ceiling is rather reflective, is white, you will send back a part of the light, and then you will obtain more uniform distribution of the light. And also we will see that when you have high quantity of light to needs, sending the light from the ceiling is much more acceptable than sending the lighting downwards, because our species has the habitude that huge quantity of light is coming from the sky. It's unusual to have the light come from the earth surface, except if you have reflections. A parameter which is very interesting also to be able to understand is the beam aperture. You have here the photometric file for this lamp, and if you put a point here, the center of the lamp, and you say that the intensity maximum is here, which is 1 to 2.5 divisions, then I am looking what is the point 1.4. 1.25 divisions is the half of the average intensity. Here I found the half of the maximum intensity there, and then I link that point with that one, and then the beam angle is Xi is given by you can measure without problem, and you see here, following the beam angle, we can classify the luminaires as narrow beam or fluid fixtures or wide fluid distribution fixtures. They are different variation about the definitions in Europe. This is European definitions, and this is American definitions. We use the same name, but not exactly the same the same flux parts. And here you have also the NEMA, which is North American also classification following the beam types. That means if you take again a manufacturer catalog, you can know exactly what is the beam spread of your fixture, but you have to be careful if you are speaking about European, American, or something else manufacturer. The curve itself is standard for all people. And well, I will go fast here because we don't speak about the sizing of the installation, and this is important for the sizing. In fact, beginning of course, some two French guys, Godfrey, propose a way to describe a fixture without using the photometric curve. And they said, why? What? They said, okay, let's assume that a fixture is 1, 2, 3, 4, corresponding to some standard angles in 3D. And then, if you know how much flux is going here, how much flux is going here plus here, how much going here plus here, etc., you can have the full description of your flux distribution in the space, and they allocate for that a number of classes going from A to J, more than A, which is very close to a projector. You have 900 over 1,000 of the flux coming in the F1 cone. If you take class A, only 267 over 1,000 parts of the flux goes in that direction, and then you can find how much go to the other directions to a cumulative way. And then using that you can classify a luminaire by using one letter from A to J, associate with an extraction efficiency, and also eventually with part T if the luminaire sends some light above. There is, in fact, if you cut the fixture in two, one upper and one lower, you can say if I have 1,000 lumens, how much lumens I will have upwards, how much lumens I will have downwards, and then I can define two efficiencies that we call the downwards efficiency, and that we call the U-lore, the upward efficiency. And then there is the way that you can describe your luminary, your fixture, and you don't need to see the curve, because you know to what corresponds. I can say this one, for example, is a class T. Yeah, I see that. Has an upward light component, and 32% of the lights goes up. And this curve here corresponds to a class E luminaire, and 68% of the flux go above. Well, if someone tell me this luminary is 068E plus 032T, I have everything what I need to make a sizing of my system without using a computer, just with pencil and paper or Excel file if you want, and a calculator. I don't need to have the IES file in that case, but to define that, those letters here, you need to have, the manufacturer need to have somewhere the IES files. Note that the sum of the two efficiencies, downward and upward, may be less than 1. Because, and this is usually the case, because that means some light is trapped inside the fixture and will never come out. Okay? Sorry? Here, because this part is class T, the upward is always T, the downward depends on the beam angle. And here, for that luminar, is class X, E. Yeah, you have 68% if you have 1,000 lumens coming out from that fixture. 608 lumens are coming down, and 320 lumens are going up. Doesn't mean, well, if you take the sum of two, here is of course 100%. This is a very good luminar. In reality, an excellent luminar, if you make the sum of those two, you will find something between 90 and 95%. Yeah, no, the yellow, the lower yellow is class E. The upper yellow is always class T. Okay? Yes, it's the same. It's the same fixture, and virtually you cut it in two. You have one part is one fixture, a virtual fixture, going up, and one other is a virtual fixture going down. The real one is the sum of two. All that they are mathematical artifacts that they allow us to make easily the calculation, and that you have to remind is that this kind of calculation have been established before using computers, by using just abacus and pencils. Yeah, this is something that I want to highlight here is all fixtures, they have markings. And those markings, they are not just for be beautiful. They have a meaning and you have to understand them. One here, the CE, is a European conformity. We will speak tomorrow about CE marking. It's compulsory in Europe. A product, if it is not marked CE, cannot penetrate the European market, is forbidden. But this CE is not certified. It's, I swear that my product is compatible with European conformity. But if me in Europe I make a verification and it is not true, then one, I ban the product, and then if you are a manufacturer located in Europe, you will have a very nice fine with several zeros. Okay? You will have a fine in lakhs minimum, but in euros. Now, if the manufacturer is located in China, forget it. Also for Europe, ROAS, but not only, is that your product doesn't contain harmful materials. No mercury, no lead, no thallium, a number of toxic materials, they are not present in that product. NF, this is special for France, means that this product is compliant with the French standard 1500, C1500, which is in fact the equivalent of IEC 1500. Okay. A neck, this is also very important. This is a real quality standard. This is not compulsory, but if you have a product, we'll discuss tomorrow about those. If you have a product marketed with that one, means that you as an industry person, as an industry manufacturer, you have an accredited laboratory inside your company, and this marking means that you respect a number of standards, and normally there is a small figure nearby, I will explain to you tomorrow, that identifies which lab is. And having a such accredited lab inside the company, it costs huge amount of money, and usually if you do that, means that your product they are really good, otherwise forget it. And this is the equivalent for US, the UL marking. I look if there is something equivalent in India. No, in India you have energy markings, but I didn't found something equivalent to that or that in India. But India most probably relies to that standard, or maybe to that one. Okay. And then you may have other signs. This one means this product cannot be to the bin. You have to give it to someone to recycle it. This one has an important heat, and it is not advised to approach more than 20 centimeters because you can be burned. And that one means this product is for indoor lighting. Okay, but those one, their quality, there is more use pictograms, and you may have many others, but this is the main that you will find here. There is an example. This is an example for ballast. You can find that either on the ballast or on the fixture. And here is the case of few ballast. Here is an old ballast from Philips, ferromagnetic one for fluorescent lamps. What you can find on the top? First, the manufacturer, the serial number and origin. This is important for tracking if there is a problem. With that number, the manufacturer can know that was a problem that day with this operator who certified the product, and they may look if other products at the same series may have the same problem. Okay, traceability. Then you have here some information concerning the lamp that you can supply with this ballast, the voltage. Here is one time TL. TL equal linear tube fluorescent lamp, 18 watt. It operates between 220 to 240 volts. This is for Europe, and it is high frequency ballast. Well, excuse me, is not a ferromagnetic. This is a ballast, high electronic ballast. Power factor 0.986. 100 milliamps, and we speak about the IP class a little bit later. I will explain you what it means, the IP class. Then other informations, you see the CE marking. This is mandatory. You see that one is certified by ENEC and the laboratory number 8. I know who is the certifier. And here you have a sign concerning the protection against fire hazard. I will explain you that later because it is important. And then you have some other information that is more necessary for the ballast manufacturer here, or the lamp manufacturer, than for the end user. This is another example. This is a low voltage DC ballast for spotlights, incandescent lamps, Philips, made in Europe, the type, what kind of lamps, show you the socket, 12 volts, 50 watt max, class 3 for the electrical protection. I will discuss also in the next slides about that. And this one the lamp can be very hot. It's an incandescent lamp. It's better to not go closer than 50 centimeters because you may have some burning effect. Let's look a little bit some of those markings closer. And the first one is the IP, the protection against penetration. What you can insert inside the fixture. And this is very important because if inside the fixture there is any electrical problem, you can be electrocuted, or you can touch something very hot and be in problems. Well, for that we use the famous IP protection rating, which is not only for lamps and fixtures, is universal for any kind of electrical products. And IP is constituted by two figures and potentially, not always, by two letters behind. The two figures here, they are independent. Here is not IP68, but it's IP68. The first one shows you what is the level of protection against solid bodies. We'll discuss here. And the second one is what is the protection against liquid penetration inside the device, inside the fixture. The first one goes from 1 to 6. 1 is completely 0, so you can have 0. 0 means completely open. You can put your hand, you can put an elephant. What you can fit inside, you can put it inside. Okay? No protection at all. 1, there is not possibility to put your hand in. In this one, I can put my hand in. It's at least 1. It's not 0 because you have here. That one, I cannot put my hand in. Okay, it's higher IP. IP2, I cannot put a finger inside. A finger of an adult. IP3, I cannot put a tool like a screwdriver, or the finger of a kid. And you pass from kid to adult at 6 years. That means if you want to eliminate kindergarten, the kids they are lower than 6 years, then if you have lights at the high of the kids, you have to take at least 3. Now if you go to the primary school, the kids are from 7 and above, then you can use class 2. Okay? It's completely stupid because 1 year doesn't make the difference, but this is the way that the standards operate. Class 4, you cannot put a wire inside. Class 5, dust cannot penetrate inside the luminaire, but it's still open. And the class 6, dust and water cannot penetrate in. Okay? Then the second one is the resistance to water penetration or liquid penetration. 1, normally you are protected if the water comes from above. If you are in the city and you have rain, if the rain comes vertically, you have some protection and you can go up with different inclinations, and then here you can go in number 5 or 6, even if you send water with a high pressure water jet to clean the luminaire, for example, from above. Here in 6, the water will not penetrate up to a very high pressure of the water jet. And here is, in the case that you have your luminaire installed in a area that may be flood, could be underground parkings or around the different the water ways and things like that. That means the luminaire can support not permanent flooding, but occasional flooding. And now, if you wanted to eliminate your swimming pool, the lights are inside the water, and then you need at least class 8 because they are in permanent inside the water. Otherwise, you know very well that water plus electricity is not a good point. Usually, inside, class 1 or 2 is fine. 0, no problem, except if you are in some industries. We'll use some examples. You are in the cities that you need to avoid dust. That means at least 5. But also you need to be able to clean the fixture one time per year by just passing under the fixture. That means today in Europe and US and other countries, and most probably here could be a nice thing to impose, you need at least IP65 for street lighting. The other letters here, they are more difficult to find, and you have the significance here. I will not in the details, but everything is given in the standards. Electrical, fire, and impact hazards. This is very important. Let's start with electrical hazard. You have 4 classes, sorry. Class 0, no protection at all. If something happens and you touch, maybe you are dead or not, but you will get a shock. Class 1, you have just a grounding wire on the metallic part. That means if you are in a TN protection configuration, that is usually in our homes or in some buildings, if a phase touch the metallic part, as the metallic part is grounded, if you touch the metallic part, you are protected. But if a second person touches the metallic part simultaneously, then you are in trouble. Okay. Class 2 is a double insulation, is not grounded. That means all the electrical high power is isolated, is disconnected from the external part of the device. This kind of lamps and fixtures, we find it nearby water points. For example, in bathrooms and things like that, nearby the water areas, you need to use this kind of double insulation. And class 3, this is only for DC low voltage up to 48 volt protection. That means here you don't have really serious hazards if you touch. Now be careful, because 48 volt, if you touch it, you will have a serious shock. And if you have water in the floor and you are not having insulating shoes, then you may be even dead. More above 20 volts when you are in the water is a huge problem. In the swimming pools, this is an obligation, okay? Unless if you want to kill some people that you invite at home. Fire hazard, this is very important. You have 2 kinds of symbol, the Fs and the Ms. Usually inside buildings, like here, you don't need any fire protection. Here is just, what means that? That means this symbol means that if there are fire inside the place, the fixture has a given resistance before melting and increasing the impact of the fire. This one you can find in place that you have different flammable materials. That one you will find in some industrial installation when you have explosion hazards. Because if there is fire, if the luminaire adds a little bit to the situation, can be very problematic. And that one is when you incorporate lamps inside tables, I don't know what, in contact with wood, to avoid to have inflammation around. And finally, the IK index, I will go very fast here. The impact hazard is what is the resistance of your material when you knock with a given power inside, with a given strength. This is very important when you have things that they can be injected to the luminaire and you can destroy it. But for example, if you go to some situations like jails, for example, you need to go to IK10 because we know very well if people there, they have the possibility to crack the fixture and take parts that they can use as arms or I don't know what. And then you have in that case, you have to have very strong devices. You can also see that, I have seen that in a French territory in New Caledonia, street lighting, they have grids on the top. And I say, why grids? Why you put grids there? What is the interest? He told me that because there are kids sending stones. I don't know what is the name of the thing with the elastic. And they are looking for the street light in order to play. And then you have to add something that can resist to such kind of shocks. There is, this is my last slide, you see, okay, I respect the time. There is three examples. We are in a meeting room. No accidental ingress issues. Unless if you have your cup of coffee and you send it intentionally or not to the luminary, you don't have anything going there. You have very little dust or not at all. Same thing also to touch the luminary, you have to get on the table, which is intentional. Negligible humidity, no risk of impacts, no explosion, no fire. In that case, IP20 is fairly enough. IK00 okay also, and just connected to the ground. Class 1 for the electrical hazard is enough. Even you overprotect here. The problem is when you have higher IPs or IKs and different class here, the price increases exponentially. Let's go here, a factory. Here you are clearing a dust environment. You can see here. You have a risk of splashing. Water can come out from the machines and go up. Probable impacts, something cutted can be projected against the luminary. Low risk of explosion in that factory here, where here it is advised to be an IP54, IK2 to resist on some kind of shocks. And it is better to have a class 2 isolate luminaires, because you may have water coming in and the luminary is not really protected against water splashing from behind. And okay, this is a good factory. In fact, you may have hazards of fire. It's better to put 1F protection for your luminaires here. And that one is a floor mile. It's also industry. You have dust in form of microparticles, and the problem is that microparticles of floor, they are explosive and even self-explosive. This you have to be very careful. You can use water jets to clean the machines, and you may have probable impacts. Here you are in severe environment. You need, as you see, IP at least 65, better 66, AK7, protected against water, and 2F for the fire, because you are really in an explosive environment. If you take a petrol station, this 2F is necessary. We can discuss about the IK because you don't have projections. You may have water, then you see, following your needs, you can select which class of luminaire you need, what class of fixture you need to install in your place in order to avoid troubles. Okay? But this doesn't say you if you illuminate correctly or not the area. That is something that we'll discuss in another lecture. Okay? Thank you. 12:30. I propose to stop here, unless if you have some questions. Yes, tomorrow. We'll discuss about standard. Tomorrow we'll have morning and afternoon. We'll discuss about control systems for energy saving standards. And the day Friday we'll discuss about environmental impacts, life cycle assessment, and most probably circular economy around lighting, which is also very important. I had another lecture how to size a lighting system, but finally I will not use it. Pradium has the slides. Today you can do it by using softwares. You will be most probably not lighting designers, and this lecture is not really needed for you. If I had 2 or 3 days more, then we can discuss about, but I would prefer to not use that one. Okay. Maybe because we have few minutes, if you agree, I can show you some that I don't show yesterday. We spoke yesterday about only LEDs, but in fact there is another way to create solid state lighting systems, is using organic LEDs. Organic LEDs, they are plastic foils that creates PN junction. In fact, you can tell me plastic is not conducting, is insulating. This is not always true. Both LEDs and organic LEDs, they are diodes, PN junctions, with the same characteristic, but organic LEDs has some different behavior that can be very interesting for some kind of applications. Here is, you can generate any kind of color, including green. Green is even the more easy to generate here, with good efficacy, with long lifespans, and as it is plastic pieces, they can be foldable, they can be fully transparent. Imagine, for example, a window that during the day allows daylight to come in, and the evening becomes a light source to illuminate your environment. And even as with organic semiconductors, we can have also organic photovoltaics. Then the window can be also photovoltaic. You can imagine things like that. The technology is still in childhood. Yeah. In fact, as I told you, plastics, they are insulators, but not all plastics. That we call the polymer conjugates, discovered in 1997 by Shirakawa and all. They are semiconductors. I will say more semi-insulators because the conductivity is really very low, but current can pass through, not to the ohmic way. There are no more continuous flow of electrons, but electrons jumping from one molecular orbital to another is not the same physical mechanism for the conductivity, but you have a conductivity, and those three guys got the Nobel Prize of Chemistry in 2000 for this discovery. And you can see here 10 years later we had a first organic LED in thin layer films by a Japanese Kido, and today we are about to have the technology penetrating the lighting market. If you take your mobile phones, top level mobile phones, the screen is no more a passive screen, but it's a organic LED. We know to produce screens with organic LEDs, It's a little bit more complicated to produce wide organic LEDs. But we are working on. You see the progress, very rapid, 2005, 50 lumen per watt, 32 in a year later, 40, up to 102 lumen per watt in 2008, and since then continue increase. We are able to make large area screens here. And here is the efficacy in lumen per watt. This is for components. You see here we are more than 100 lumen per watt, and this is organic LED systems that is also increasing very rapidly. Then you can tell me, do organic LEDs one day will replace LEDs? The answer is no, because they don't have the same properties. For that one, yes, because to get a so big light here, you have the LEDs all around, and you need a diffuser in order to get uniform extraction of the light. An organic LED can be emitting for all that surface with a single organic LED. For interior lighting, maybe organic LEDs can be more interesting than playing with this kind of LEDs. And you see also that the cost is decreasing. We are going to go the right direction. There is the way that they work. You have a substrate that can be a thin part of glass, or can be a plastic, PET, or plexiglass, or can be even metal, what you want, or even tissue. You have different options. Then you have an anode made by indium tin oxide, and then you have on the top an organic stack that creates the PN junction. I will show you how. And on the top you have a second electrode in order to create the electrical contacts. And there is the way that it works. You have the cathode, you inject electrons here, then you have a plastic layer that allows to the electrons to go to one direction. You have an emissive layer here, and from the other electron you inject holes. You have a hole transport layer that allows to the holes to arrive in the emitting layer, and in the emitting layer the holes will meet electrons. You have annihilation, and the difference is going out as light. And that you can do it as you want. You can have top emitting, down emitting, or fully transparent devices. Well, in the paper seems easy. To achieve that one is very complicated, but it is doable. Yeah, two technologies. We use that we call more often the small molecules. In my laboratory we are making some organic LEDs. And what is funny here, this kind of organic molecules, they are very similar, geometrically speaking, to the molecule of chlorophyll. Chlorophyll is a ring like that one, much bigger, with a magnesium in the center. And chlorophyll is the photovoltaic for the plants. Chlorophyll just get light and generate voltage, that energy that the plant can use for the other operations. Okay, we try to make LEDs using chlorophyll, but we obtain infrared emission, and infrared is not so interesting for lighting, of course. And then you have polymers, and as you can see here, you can obtain any potential colors, especially when you change the polymer length. You change the gap, and you can get any kind of color. blue, yellow, green, red. Potentially UV, but usually UV plastics, they don't like UV, and infrared without problem. And in fact, this is the way that your system works. You have that we call the p-conjugate molecules, that they have these orbitals with this specific structure, and what happened? One electron attached to that orbital, and then will transmit with a jump to the next molecule which is nearby, passing from one orbital to the other by jumping, not with continuous thing. There is the way to generate white light, same thing. Organic LEDs generate color light, but you can mix and you have much more possibilities to create a white light than with LEDs. How you can manufacture? Different ways. Evaporation, this is my own system in Toulouse. You evaporate molecules and you create thin layers of the different films. You can use spin coating. You use the viscosity of the material to create thin layers. We are speaking here about layers with less than microns, okay? Less than 1 micron. You can use also the doctor's blade, same thing. You can do ink printing, and maybe one day we'll be able to make ink printing like a journal paper continuously in huge size, and the day that we can do that, the price will really go down, and it will be very easy to use this kind of lamps by using offset serigraphy. Well, some funny applications around lighting. Always we start with decoration. Here, that you see here, they are OLEDs here also. And in fact, this mirror is a smart mirror, has a camera somewhere. It locates the image on the mirror, the image of the lady, and switch off the OLEDs. You can see your image without problem, and you are eliminated by the OLEDs here. The fact that you have a large surface, you can generate much flux, but large surface means low brightness, and low brightness means no glare. The lady has no glare problems here. This one, more fancy, Christmas trees from GE, an OLED pillow. I don't like the idea because blue light is not good for sleep, but okay. And also a wedding dress. I don't know how much it cost. Well, most probably you cannot find it. This is, yeah. There are some potential applications in transport. Inside trains, for example, you can have the windows becoming screens. In cars, in aircrafts, we can imagine aircrafts with no more windows, because when you open windows, you fragilize the structure, and you can imagine that the aircraft is completely covered with OLEDs, and then you can have cameras above and beyond, and you can have a projection of the sky image, and you have the impression to be flying without anything else, like in Aladdin's carpet. But well, for the cars also it's interesting, because here is an idea to have this kind of cap with OLEDs, and in fact, when you brake, all the cap becomes red. When you put your flash, a part of the cap becomes yellow, and this allows to see the car from much further. All that are ideas, of course. This is not more ideas. They have. This is the first task lamp with OLEDs. It's leaf here is an OLED, a single OLED by Ingo Mauer. Here you have some OLEDs in a NEC office, Koizumi, and this is Matsushita also, and that one is much more fancy. Is by a French company named Kinetics. In fact, you have Each piece here is one OLED, and not only you can switch on and off or dim, but also all the thing can move, and you have the impression to have moving light waves. Okay. And just to remind you that if I have a single 1 meter OLED device with luminance of 1500 candela per square meter, which is very low, you cannot be glared by that, then you can obtain 300 to 400 lux on the table, what is requested by the. I remind you that Kido was the guy who produced the first white organic LED. And this is the OLED's cafe of Kido. He was going from exposition, from expo to expo with his OLED cafe. Everything inside is illuminated by OLEDs. And this is also in a Japanese company with moving fixtures. And you see it's absolutely thin, because here the source is just few microns, even not. That means, and you don't have so much power, thermal power to evacuate. Here the efficiency is very high, and you have very thin stuff, and this is very, very interesting. Other ideas. This is the universal display kitchen. Here is some configuration for black body company, that you can see different kind of lightings. You can really imagine what lighting designers can do with something that can be folded and take any shape. However, the technology is still under improvement. There are many things to look. For example, the black spots can appear. We don't really why those black spot appears. Maybe ohmic effects due to micro spikes inside the different surface that are covered with plastic. You can have crackings. You can have spatial non-uniformities, and in fact, you need different things to do. And something that is interesting is you can use biosource materials from crops. For example, in my team, we create small organic LEDs that 40% of the organic matter inside is coming from carrots, beta-carotene. And recently we add some other materials from spices. Yes, it works. And we got very nice white light. I told that we can add some beans or pea and get a soup after, but everything is possible. Some other SSL technologies. One is using lasers instead of blue LEDs. This is something that is working very well today in cars. You can see here an example. The piece of the phosphor that I showed you is that one. And behind here, you have a 2 watt blue laser diode, and you can see how much light you get here. You have different options. This is something that we use more and more today in car headlights, and we also use it for connected light, because with lasers you can modulate the light and transmit information through Wi-Fi. This is another option, electroluminescent device. This is very old, it's from 50s. It's electroluminescence, but here is a passive electroluminescence. In fact, you have 2 electrodes, and inside you have a layer of an oxide that you can excite at very high voltage. We're speaking about more 1 kilovolt, and very high frequency in AC. This is AC, and this is the stripes that you can see, for example, inside aircrafts or inside different places that you need to guide people through the exit. Is used mainly for security lighting. And the last crazy idea is that one, use bioluminescence. Excellent, zero electricity, but you need to feed algae, different kind of organism, bacteria, and things like that. Okay. Some guys tell, okay, we can play with the genes of trees and make the trees luminescent, and in that case you can have like algae, and you can have a light for free in the night. This is a truly bad, not another one idea, because if you want to have a genetically modified organism in freedom around of you, go to that way. We don't know really what can be the final objective and what you can get with that. Now, you can in some cases, in some tunnels, that is very difficult to have security lighting. You may add some bottles with natural algae that they produce light without electricity, and use the CO2 in order to feed them. But you need to have maintenance, and in the case of electrical shutdown, you can still see your way. Maybe some application can be acceptable, but that one is no. You have many people speaking about that. The answer is no, and definitively no. Yeah. And then that way I completely finalize what I want to say about light sources. But as we had time, I show you that today. Yeah. We can stop here, unless if you have any questions. Yeah. Sorry? I use the mic.
Thermal stability of OLEDs.
Yeah.
What is that thermal stability?
The thermal stability of OLEDs is better than for LEDs. In fact, when the temperature increase, the efficiency increase also. The problem is that as you have plastic things, you cannot go to temperatures higher than 78 degrees C, otherwise it will melt. But the behavior is better for organic LEDs than for LEDs.
Okay.
When you see large TV sets that they are with organic LEDs today, they don't have radiators behind. They don't need a radiator because we keep the temperature low enough in order to protect the plastics.
Okay. Thank you.
They are not concurrent to classic LEDs. They can target something that is different.